Looks okay, finally. Okay, so in this presentation, basically, I'm going to talk about the system that I used yesterday during the performance, and the piece was called One at a Time by Voice, and the system I use, I just call it voice control interface for digital musical instruments. So, as most of you, I think, may know very well, when we want to interact with digital musical instruments, nowadays we really have a variety of choice. I mean, the choice is really big. We can find many devices on the market, and there's like hundreds and hundreds of prototypes around. And if we are still unhappy with them, we can just like build our own interface. I don't really want to go into details of interfaces, but if we look at them, all of them share something. So the input modality, in particular, it's kind of like redundant. This one means that you still need to use your hands to interact with the majority of these interfaces. And nothing wrong with that. I mean, I'm pretty happy with using my hand because I think they're very reliable, and at the same time they're expressive. But we have a limit. We are limited to the number of two, so we have only two hands. So if we want to use more than one interface at the same time, we may have issues just because we are limited by our body. At the same time, if we look at performances based on electronic or digital musical instruments, you may see that most of the time the performer is not using his voice. So we can identify the voice as a spare bandwidth. And the idea is to use it to allocate extra musical intention. The good point about using voice is that it's an independent source of information. It means that whatever we do with our body and whatever we say, it doesn't have to be linked. And another good point is that using the voice at the same time you use your body, it doesn't really require you high attention or concentration. An example is that when you drive your car, your body is fully engaged with your car, but you can have a conversation or you can sing at the same time. And this one doesn't really require you a specific training. Actually, we are already trained to do that since we are born. Limitation of voice-driven system, voice control, is that this system, for different reasons, they can be affected by noise, by feedback, or the latency can be too high. So usually, if we look at everything that can be driven by voice, is never allocated to the so-called mission critical task. Going back to the example of the car, you may change radio station, so you can interact with the infotainment system. You don't really decide whether the car is going left or right by voice. For that kind of like critical things, you still use hand interaction. So let's try to digest all this concept and to apply to musical performances. The idea here is to use voice to drive, and this one in a certain way is a contradiction with what I did yesterday, but we will see it later, to drive an arbitrary number of real valued and time continuous parameters of any digital musical instruments. Because in my opinion, there are less mission critical. What I define mission critical musical performances are those commands that you send to an instrument that need to be very precise on a discrete grid in time and frequency domain. So technically notes. If you play the wrong note, you may end up corrupting the harmony, the melody, the rhythm. So the audience perceive it as an error. If you're not really precise when you're playing around, I don't know, with cutoff frequency and resonance of a filter, if you're a little bit late or not really precise, it can still be okay in some performances. The level of abstraction of this interface is very low because I want the latency to be as little as possible. So basically it works at the level of the voice timbre, very close to the sound abstraction level. And the mapping is based on a bunch of machine learning techniques for two reasons. The first reason is that doing it by hand is going to be tough. And even because I want to minimize the time that the user has to spend in setting up the system. So if machine learning can do most of the job by itself, actually, it's better. And compared to previous work, because this is not the first time that someone tried to use voice to interact with instruments. Compared to previous work, here I aim to be holistic. That means that this system can be used with any instruments and with any vocal gesture, and we will see later what I mean with this, and adaptive. So it means that the system by itself is able to adapt itself towards the performer voice characteristic and to the characteristic of the instrument. So from the audience perspective, especially if you saw the performance yesterday, you see a microphone, there's voice going in, and the sound is coming out from the speakers. But actually, it's not an audio effect, sound processing, or whatever. Actually, things in the middle gets really broken down to low-level parameters, to low-level commands that then are sent to a completely independent instrument that re-synthesize from scratch the sound. From a user perspective, the system looks like this. The user just needs to provide to the system a bunch of vocal examples, the instrument that you want to control, and the system generates automatically a mapping. What's inside this mapping? There's going to be some information more related, let's say, to the voice, some information more related to the instruments. And actually, I'm not really mapping one into the other, but I'm doing an intermediate transformation to a to a simple, fixed, and well-defined space that in my case would be any uniformly distributed hypercube. And the advantage is that I can keep things separated in the training part and also the mapping, in the real-time mapping. I'm going to have two layers. One layer that does the mapping, the voice-related mapping, and another layer related to the instruments. And I can exchange only one side of it during my performance. So I can keep one side, changing the other side, and vice versa. This is the bigger picture. I don't have enough time to go into all the details. I just want to show you that on the top part, that is the learning part, there's going to be something that tries to figure out some information from the voice example provided by the user. Another part that tries to study the way the instrument reacts when we change some of the synthesis or processing parameters. And this information are used in the runtime part. So let's talk about the instrument first. What is an instrument in this context? It's any device that any deterministic device that generates or process sound. So either a synthesizer or an effect. In real, when we perform with an instrument, usually, even if we have like hundreds of synthesis parameters available, we are not really interested, or probably we are not even capable of thinking to control all of them. So usually, when we perform, we select only few parameters that we want to control. The user just has to give this information to the system, and he has to provide the instruments to the system. So the system by itself, it takes care about generating all the possible input combination of those parameters. For every single combination, it generates the sound, it analyzes the sound, computing some, let's say, perceptual related acoustic features. And then these features are post-processed. This post-processing, it kind of like depends by the way the user, the performer, want to analyze or consider the instruments. This can be for generator, so it can look only at the sustained phase, making an average of the feature. It can look at the dynamic over the sustained phase, or it can look at the entire attack, decay, release envelope. This one is for generator. For processors, I can compute a bunch of like features that are more related to the time domain. So actually I'm looking at doing some post-processing over the impulse response, or I can feed the processor with noise at the input and doing a more frequency domain oriented analysis. However, in any case, I will end up with a high dimensional space with a bunch of points in high dimensional space that represent how the sound of the instrument change when I change those parameters. So what I do at first, I reduce the dimensionality to the effective dimensionality, so to the embedded dimensionality, using nonlinear technique. And I end up, let's say, in 3 dimensions with a bunch of points over a space. Here, the issue is that the number of points, the dimensionality, the distribution, and the shape can be arbitrary. So time by time, instrument by instrument, I don't know what to expect. So what I do here, that actually is something I'm using the same algorithm that Diemo mentioned before. I'm transforming this space into a uniformly distributed hypercube. Okay, in 3D it's going to be actually a cube, but this approach, it works with any dimensionality. with this algorithm that actually maintain the same neighborhood relationship between points. That one is very important. And what I'm doing after, I'm learning this transformation with a neural network, basically doing a nonlinear regression. So how's the interface gonna work is that I can imagine that my voice, so even if I don't use voice, I can control instrument using this technique. My gesture, so my gestural input will give me a coordinate into this space. Using the neural network, this coordinate get translated into the other space. I will go and find what is the closer point, and every single point on that space was generated by a unique combination of synthesis or processing parameter. I just get back, I say, okay, what was the combination? Was that one? I send it in real time to the instrument. Actually, the search is a bit more complicated, but this one is just to show you the concept. Let's talk about the voice. Two very basic principles of this interface. When the voice do not change over time, the parameters should not change over time. And that's what I call the vocal posture. So posture is a kind of like absence of movement. On the opposite, a vocal gesture, that can be any sequence of voice and unvoiced sound. When I provide to the interface, when I present a vocal gesture to the interface, in some way, the parameters should change. So here we have like two examples of the a vocal posture that is just a vowel. Okay, I don't have sound. Okay, I'll try to play from these speakers. This is an example of a posture, so vocal sound that is not evolving over time. And for a gesture here, for example, there is a gliding between different vowels, so it's going to be a movement into the vowel space. When I look at the gesture, for instance, let's take as an example gliding between three different vowels. I'm not really interested in the temporal unfolding, so I don't really care about how things happen in the time domain, because time in a certain way will give me only a monodimensional output. What I'm more interested in is the way this vocal gesture unfold spatially, so even in high dimensional space, how things are organized. And as you can imagine, I'm going to use movement into this space to browse the sonic space that I generated from the instrument. Problems and challenges here is that there are a lot of variabilities involved in any voice-driven system, and here as well. So differences between the same speakers, the same speaker, different across speakers, difference across different hardware, so different microphones that I can use. The same speaker, the same performer may want to use different vocal gesture time by time. And then another question is that whenever we do like speech analysis or whatever, I mean, you never know which computation parameter will give you the best result, and what can be and how can you define the best. So for instance, which window size should I use, which order of computing features, which category of features, and so on. So how does it work? At first, the user has to provide examples. The better, the more, the better, as usual. But it doesn't have to be so much. So from a set of vocal postures and a set of consistent vocal gesture, the system iterates across hundreds of different combinations of parameters to compute the features. As features, I compute LPC, MFCC, and PLP all together. Even if they are very redundant, at the moment I really don't care. So I iterate over hundreds of combinations of computing these features, so different sampling rate, different window size, and so on. And I try to figure out which one is the best, computing some quality metric. And at the same time, I generate a mask. Actually, it helped me to select those features that are not noisy over the posture. So I want features that, when I'm doing a vocal posture, my features should be stable over time. Then, looking only at the vocal gesture examples, I compute the features, I do the filtering, so I remove the features that I want to use, some outlier and clustering analysis, and let's say that I end up with a space, like the one you can see on the left. This one is in the 2D case, but the same principle applies in 3D, 4D, and so on. So what I do here, I use a modified version of the self-organizing map algorithm that I call the self-organized gesture. It's a slight modification to avoid basically that the SOM is going to fold on itself, and it makes sure that it's kind of like is well spread over the gestural space. I learned this lattice structure that is actually an SOM, but actually here I'm representing the SOM into the original feature space. So actually those one are the weights of the output nodes. Here there should be like an example of this training procedure. Actually the modified algorithm, it tries to pull things over 4 corners in 2D and try to pull things over 8 corners in 3D to make sure that things doesn't fold on itself. So here you just see this is the initial condition, and you're gonna see the result, because the training in 3D takes much longer. So in any case, how I'm gonna use this structure? So basically here the SOM helped me to learn how this 2D, 3D space that contains my vocal gesture unfold and expand, how the dynamics are basically compressing and expanding. And I'm not going to use the SOM to do recognition or classification, but just to pick the relative index on the grid of the closer node. So my voice when you use the interface, after computing the features, all the pre-processing you need to do, is going to be 1 point into this space, the yellow point. So as the output of this vocal gestural controller, it will be the index over the grid of the closer node. This one will give me a limited resolution, so I can get the closer nodes and make interpolation using indirect distance weighting. And as a search space, usually I do not search across the entire lattice, but I shrink it to the Moore neighborhood, because I want movement and transition to be more smooth. So if the new point ends up being up there, it's going to iterate state by state, and it's going to reach that point. So it's going to provide me a more smooth movement from one point to another point. Okay, the runtime part, as you can see, there are 2 layers, one related to the voice, one related to the instrument. The connection between the 2 layers, it happened into this virtually into this uniformly distributed hypercube, and is a linear 1-to-1 mapping. So just to summarize what happened in a simple 2D case, from the voice I compute the features, I do dimensionality reduction, I end up into that space. I pick the node of the closer node that will be ideally distributed, ideally be 1 point into that space. I change coordinate with a neural network, and I end up into the sonic space of my instrument. That is the red point. And I make a search not across the entire space, but I search only, in this case, only across the blue points that are neighbors, not in this space, but they are neighbors in the parameter space. In this way, actually, I'm going to avoid big jumps into the parameters that I generate for the synthesizer, because it's possible, it can happen, and actually it happened pretty often, that completely different parameters sent to an instrument generate similar sound. It can happen, and this one will give me discontinuities, and I want to avoid this, so I shrink the search to a subspace of that space. Okay, I make the search, take the parameters, and I send it to the instrument. Optionally, my system generates a note, so basically MIDI note, looking only at energy, pitch, and onset detection from the voice. That is a contradiction with what I said before about what is mission critical in musical performances. But I decided to do that, and it's not even that elaborated, that section in the prototype, because I want my performance to be completely based on voice. I didn't want to press buttons or play with a keyboard at the same time, because then probably for the audience it's going to be more difficult to understand what was mapped on the voice and what was mapped on the keyboard and whatever. And these 3 spaces are provided in real time as a visual feedback, even if for performing I kind of like try to memorize it, and I use only the one in the center to kind of like figure out whether the system is working and is responding. So yesterday I have that kind of like matrix of baton that have also like LED on the back, LED on the back. So I was just like looking at my coordinate into this 2D space by the position on this LED matrix, and actually the 3rd dimension was color coded. Okay, the prototype is implemented in Max for Live, and MATLAB. This is a screenshot of the part that makes the instrument analysis, and those three little devices are the front end and back end, so I can host my instrument in Ableton Live without needing to develop any external piece of software. The learning phase is mostly done by MATLAB script, so it's offline, and the runtime part is run by this Max patch here, and two parallel jobs in MATLAB. So there are two concurrent and parallel jobs running in MATLAB. Each job is doing one half of the mapping. So there is one layer, one job doing the voice mapping, another one doing the instrument mapping, and communication between Max and MATLAB is implemented in Open Sound Control. Something that I didn't specify is that, but actually I think was a bit obvious probably, is that the machine learning that I'm using is unsupervised. So the user never had the chance to specify, I want this map to this. This choice, I went on this way for two reasons. The first is that generating supervised machine learning data, so the data that you have to feed to the machine learning, sometimes is like tiring. I mean, you really have to provide a lot of data. And then, because if you're not really familiar with that specific technique, you don't know if you're asking to the machine learning to learn something that is learnable. So you may ask to the machine to learn something that is impossible to learn, especially for a specific algorithm. So I prefer to go for unsupervised learning. That means that when the mapping is ready, then is the time for the user to use the system and learn what the machine learning has learned before from the data. If he doesn't like the way the mapping was implemented automatically, here there's all the options that are available on the prototype to do some fine-tuning, and there's no need to retrain the system. All these options work in real time. So options about the voice layer, the instrument layer, 3 different gates to enable, disable the system based on 3 different vocal features, optional behavior of the instrument when the gates are closed, and this is the option for the note generator. Few words about the performance. I modified the prototype in order that instead of working with one voice map and one instrument map, it worked with 2 banks. And every time I press a button, I just select a different preset. Every preset is select a pair of map, and it reconfigures in less than a second the system. Together with selecting a specific instrument in Ableton Live and some option like on which track is it, the value of the quantization, and optionally I can record the parameters and MIDI coming from the interface into the timeline of Live. So basically, I can control one instrument at a time. I can optionally decide to record it on the timeline. So layer by layer, I build the improvised composition. So few consideration about this work. Okay, usually the number one question I get about this system is about noise, feedback from the microphone, and we can discuss probably about this later. I mean, it's a bit complex. I mean, yesterday I was not using any noise reduction, feedback, echo cancellation, whatever. I didn't have any specific problem. I can tell you that noise, feedback from the speaker, it can give me some problem with the noise, with the note generator. But the other part, the controlling the parameters, doesn't have really many problem with noise and loud music in the venue. I ran a study that involved 10 users, and all of them agree with me that this one actually is not supposed to be an alternative to traditional interfaces. It's supposed to be an extension. So you do something with your hands. At the same time, when you need another hand, you do something with your voice. That is another contradiction with my performance. And practicing is necessary, and the visual feedback, so looking at the voice space, the instrument space, play a central role in learning how to use it, and it's not easy. I don't think it's an easy interface to use. You have to practice a little bit. It's not one of those things that you take it out of the box, you plug it, and everyone can do the same. So it's kind of like it was designed in a certain way to promote the virtuosity of performer. So if you practice a lot, if you master your skill, you can do better than another person. And that's it. Few words about like future work. I'm not really. I mean, the system is more or less fine as it is. I'm just changing the way I have visual feedback. So I was thinking to put a tiny little LCD screen in front of the mic, or probably to wear it here. And all the hand interaction that I need is just like a rotary encoder and 2 buttons. So that one is going to be the bare minimum I need to use. I need to do this performance. That's it.
Thank you very much, Stefano.
Welcome.
Nice presentation.
Thank you.
I have a question. I'll go first.
Yeah.
So,